Fine. Let's start. Number 10. The Death Star next door. There's a star about 8,000 light-years from Earth that astronomers quietly nicknamed the Death Star. Not because it's dramatic, because it might actually kill us. It's called WR104, and it sits in the constellation Sagittarius, spinning a beautiful pinwheel of dust into space every 220 days like a cosmic sprinkler. The pinwheel is gorgeous. It's also the thing that scared everyone. When astronomers first imaged it at the Keck Observatory in 1999, they noticed the spiral was facing us almost perfectly head-on, like looking straight down at someone spinning a garden hose above their head. And here's why that matters. WR104 is a Wolf-Rayet star. That's a specific class of massive dying star that astronomers describe, and this is an actual quote from a scientist, as ticking bombs. When one of these things finally collapses, it can release a gamma-ray burst, a focused beam of radiation so intense that if it hits a planet, it can strip away the ozone layer and cook the surface from the outside in. And because the pinwheel was face-on, it looked very much like the poles of the star. The barrels of the gun were aimed directly at us. At 8,000 light-years away, a direct hit wouldn't vaporize Earth. It would do something slower and worse. Physicist Adrian Malott estimated that even a 10-second burst from that distance could destroy roughly a quarter of our ozone layer. You'd see food chain collapse, ocean die-offs, agricultural failure, extinctions plural. But here's the thing. In March of 2025, astronomers at Keck finally got a definitive look at the system using 3 instruments simultaneously, and they found something unexpected. The orbital plane of the 2 stars is tilted 30 to 40 degrees away from us. The gun isn't pointed at us after all. The burst, if it happens, will sail harmlessly into empty space. We're safe. Probably. But the study that saved us also broke something. Because here's what doesn't make sense. If the stars are tilted 30 to 40 degrees off axis, why does the dust spiral look perfectly face-on? Those two things are physically contradictory. The geometry doesn't add up. Lead astronomer Grant Hill put it plainly when he said the universe had surprised him. He went in expecting a simple confirmation and came out with a mystery he couldn't explain. We don't fully understand what we're looking at. We just know it's probably not going to kill us. For now. The universe has a funny way of being both reassuring and deeply unsettling at the same time. Number 9. The Forge. On August 17, 2017, at 12:41 in the afternoon Eastern Time, a pair of dead stars, each one roughly the mass of our sun, compressed into an object the size of a city, finished a death spiral that had been going on for millions of years and slammed into each other at a significant fraction of the speed of light, 130 million light-years away. The resulting explosion was watched by 70 observatories on 7 continents and in space simultaneously. It was the most observed single event in the history of astronomy. And here's what came out of it: gold, platinum, uranium, every heavy element that ordinary stars can't make. They were forged in that collision, in the insane heat and pressure of 2 neutron stars tearing each other apart. And they were flung outward at 20% the speed of light, 1/5 of the maximum speed anything can travel, spreading across space in a radioactive cloud that glowed first blue, then red, then infrared as it cooled over the following days. The event was called a kilonova. Theorists had predicted it for decades. They had detailed models of what it should look like, what colors it would cycle through, how fast it would fade, what chemical signatures it would leave in the light. When the data came back, it matched, almost perfectly. One astrophysicist described that moment as Judgment Day for the theorists. 40 years of speculation confirmed in a single afternoon. But take a moment with what this actually means. Every gold ring you've ever seen, every piece of platinum jewelry, every heavy element in your body that wasn't forged in a standard stellar furnace, it came from something like this. From 2 city-sized remnants of dead stars, spiraling together for millions of years and then annihilating each other in an explosion visible across 100 million light-years. Your wedding ring is the debris of a catastrophe. Violence, on a long enough time scale, makes beautiful things. Number 8. The Bullet from Nowhere. On the night of October 15, 1991, a camera in the Utah desert called the Fly's Eye set up by the University of Utah on a military proving ground, detected something that should not exist. A particle. A single subatomic particle. Traveling at a speed so close to the speed of light that the difference was essentially meaningless. And it hit Earth's upper atmosphere carrying 320 exa-electron volts of energy. For comparison, the Large Hadron Collider, the most powerful particle accelerator humans have ever built, a machine 17 miles in circumference that costs roughly $5 billion, can push a proton to about 14 tera-electron volts. This particle carried 40 million times more energy than that, in a single particle, smaller than an atom. The kinetic energy was roughly equivalent to a baseball thrown at a reasonable pitching speed, which sounds underwhelming. Until you realize we're talking about a subatomic particle carrying that much energy. That's not physics. That's physics having some kind of episode. Physicists called it the oh my god particle. That's the actual name in the scientific literature. Because there was no polite way to describe it. Here's the problem. A particle that energetic cannot travel across the universe. There's a theoretical limit called the Greisen-Zatsepin-Kuzmin cutoff, the GZK limit, which describes the maximum energy a cosmic ray proton can have and still make it to us from a distant source without getting eaten alive by interactions with the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space. The oh my god particle exceeded that limit. It shouldn't have been here. And when astronomers traced its trajectory back to find where it came from, they found nothing capable of producing it. Now, 34 years later, the mystery has a companion. In May of 2021, the telescope array, 507 detectors spread across 700 square kilometers of Utah desert, caught another one. Named the Amaterasu particle after the Japanese sun goddess. 244 exa-electron volts, the most energetic cosmic ray detected since the oh my god particle itself. They traced it back to its origin point in the sky. It came from a void, an empty region of space, a place where essentially nothing is known to exist that could have produced it. Study co-author John Bells, a professor at the University of Utah, said in an interview, "It could be defects in the structure of space-time, colliding cosmic strings. I'm just spitballing crazy ideas that people are coming up with because there's not a conventional explanation." That's a scientist, spitballing, about space-time defects. Something out there is producing the most energetic particles in the known universe. We have no idea what it is, where it is, or how it does it. And every few decades, one of those particles finds us. Number 7. The hum. In June of 2023, 5 separate scientific teams in North America, Europe, Australia, India, and China published papers simultaneously. They had been working in parallel for years, and they all arrived at the same conclusion at roughly the same time. The entire universe is humming. Not metaphorically, there is a low-frequency gravitational wave background permeating all of space, a constant slow rippling of space-time itself, with wavelengths measured not in meters or kilometers, but in light years. The whole fabric of the universe is being gently, continuously squeezed and stretched by something. The most likely source is pairs of supermassive black holes, objects containing billions of solar masses each, slowly spiraling toward each other at the centers of distant merging galaxies, their orbital dance generating gravitational waves that ripple outward across the cosmos and overlap and interfere with each other until they create this background hum that fills everything. But here's what stops you cold when you actually think about it. To detect these waves, the scientists didn't build a detector. There is no instrument on Earth sensitive enough. Instead, they used the Milky Way itself. They found an array of millisecond pulsars, dead stars that rotate hundreds of times per second and emit radio pulses with the regularity of atomic clocks, and they monitored them for years, watching for tiny deviations in the timing of those pulses that would indicate space-time between us, and the pulsar was being stretched or compressed. Their detector was 100,000 light-years wide. The Milky Way is a gravitational wave observatory. We just had to realize it. And the source of the hum might not be black holes at all. One of the alternative explanations that the data cannot currently rule out is cosmic strings, theoretical one-dimensional cracks in the fabric of space formed in the first fraction of a second after the Big Bang when the fundamental forces separated from each other, like fractures forming in ice as it freezes, thinner than a proton, then a potentially heavier than a mountain range per meter of length, still here, invisible, threading through the universe, vibrating. The universe has a background noise. We just learned to hear it, and we're still not sure what's making it. Number 6. The Naked Eye Apocalypse. March 19th, 2008, 2:12 in the morning, Eastern Time. NASA's Swift satellite, a telescope in low Earth orbit dedicated to detecting gamma-ray bursts, triggered an alert. On the other side of the observable universe, 7.5 billion light-years away, in the direction of the constellation Bootes, a star had just died. Not a quiet death. It collapsed into a black hole and fired a beam of gamma rays, a relativistic jet of pure energy that happened to be aimed almost exactly at Earth. The burst lasted about 30 seconds at peak optical brightness. If you had been outside that night under a dark sky looking in roughly the right direction, you would have seen it. With your eyes. A pinpoint of light, magnitude 5.3, briefly visible in a part of the sky where nothing had been before. From 7.5 billion light-years away. From before the Earth existed, visible to the naked human eye. It remains the most luminous optical event ever recorded. For those 30 seconds, that single dying star was as bright as 10 million galaxies combined. Now here's where this becomes something other than a beautiful story about astronomy. The beam hit us from 7.5 billion light-years away, and we could see it with our eyes. A similar event inside our own galaxy, aimed at us, would not be a curiosity. The gamma rays would interact with our atmosphere and trigger a cascade of chemical reactions that would destroy a significant fraction of the ozone layer. Estimates run as high as 25% depletion from a 10-second burst. Compare that to the ozone hole caused by decades of human industrial activity, about 3 to 4% at its worst. A galactic gamma ray burst, direct hit, would dwarf that by an order of magnitude. Ocean food chains would collapse. Agriculture would fail. Extinction, plural, large scale, would follow. The universe fired this weapon on March 19th, 2008. It was aimed at us by pure chance. It came from so far away that the intensity by the time it reached us was entirely harmless. We happened to be downrange. That's the thing about gamma ray bursts. They're directional. They fire in two narrow beams along a dying star's poles. Whether they're aimed at something that matters is random. Completely random. And they happen, on average, somewhere in the observable universe roughly once a day. The universe fires this weapon every day. We just hope it keeps missing. Number 5, the thing that blinded our telescopes. December 27th, 2004. The day after Christmas. On the far side of the Milky Way, 50,000 light-years away, the maximum distance you can be from Earth and still be inside our own galaxy, a magnetic field snapped. That's the most technically accurate way to describe it. A magnetar called SGR 1806-20 experienced what astronomers call a giant flare. A sudden rearrangement of its magnetic field, possibly triggered by a starquake in its crystalline crust, released an amount of energy that is genuinely difficult to put into language. In 0.2 seconds, a fifth of a second, faster than a blink, it released more energy than our sun produces in 250,000 years. That energy traveled across 50,000 light-years of space, and when it arrived at Earth, it was still powerful enough to measurably ionize the upper atmosphere. Earth's ionosphere, the electrically charged layer that makes long-distance radio communication possible, was disturbed. Radio blackouts were reported on the daylit side of Earth, not caused by a solar flare. Caused by a star 50,000 light-years away. The first thing that told us something unusual had happened wasn't data from a telescope. It was satellites entering safe mode. The instruments built specifically to observe the most extreme phenomena in the universe were overwhelmed and shut themselves down. The telescopes blinked. SGR 1806-20. Itself is smaller than Manhattan. It has a magnetic field roughly 10 trillion times stronger than a standard refrigerator magnet. It has the mass of the sun compressed into a sphere about 20 kilometers across, and the event that affected Earth's ionosphere was, in the context of magnetar physics, relatively routine. Here's the part that lingers. Only 3 confirmed giant magnetar flares have been detected from within the Milky Way since 1979. We don't know how many have happened that weren't aimed at us. We don't know how many happened in directions we couldn't measure. We know that the one on December 27th, 2004 was pointed more or less toward Earth, which is why we felt it. The other thing we know, if SGR 1806-20 had been 10 light-years away instead of 50,000, the energy flux at Earth would have been unimaginably higher. The comparison is roughly equivalent to the difference between standing next to a bonfire and standing inside it, an object smaller than a city. A magnetic field no instrument we have can replicate, a burst that lasted a fifth of a second and reached us across the entire width of our galaxy. It already happened to us. That's the part that's hard to shake. This isn't theoretical, it already happened. Number 4. The matter that eats matter. In the 1980s, a physicist named Edward Witten, one of the most respected theoretical physicists alive, the kind of person other physicists describe as operating on a different level, published a paper proposing something quietly alarming. He suggested that ordinary matter, the stuff everything is made of, might not be the most stable form matter can take. Inside neutron stars, the collapsed remnants of massive stars, where a teaspoon of material would weigh about 1 billion tons, the pressure is so extreme that protons and neutrons can't hold themselves together. They dissolve into their constituent quarks, up quarks and down quarks, floating free in a soup. And under those conditions, Witten suggested something interesting might happen. Some of those down quarks can spontaneously convert into strange quarks, a heavier, rarer variety, and the resulting mixture of up, down, and strange quarks might actually be more stable than ordinary nuclear matter. The thing is, nature always seeks the lowest energy state. Water flows downhill, atoms form molecules. If strange quark matter really is more stable than ordinary matter, then ordinary matter is, technically speaking, sitting at the top of a hill. It hasn't rolled down yet because the energy barrier to convert is enormous. But if you gave it a nudge, if you introduced a piece of already converted strange quark matter, called a strangelet, the surrounding normal matter would want to convert too. And it would. And then that converted matter would convert the matter next to it, and so on. Edward Farhi at MIT described it plainly. If strange matter formed in the core of a neutron star, he said, it would eat its way out and consume the entire star. You'd end up with a strange star, an entirely different category of object. And if a piece of that, a strangelet, potentially microscopic, potentially the size of an atomic nucleus, if one of those made it out into space and hit a planet, the planet would convert. Slowly at first, then faster. The whole thing eventually compressed into a cold, dense lump of strange matter the size of a mountain. By the late 1990s, this had stopped being a purely theoretical concern. Brookhaven National Laboratory in New York was preparing to switch on a collider called RHIC, the Relativistic Heavy Ion Collider, which would smash gold nuclei together at close to the speed of light. Someone asked whether that could produce a strange lay. And then someone asked whether that strange lay could destroy the Earth. There were formal safety reviews. This wasn't fringe concern. This was serious people asking serious questions. The conclusion that cleared RHIC to operate was not a theoretical argument. It was an empirical one. The universe, it turns out, has been running this experiment continuously for billions of years. Cosmic rays, high-energy particles from space, slam into neutron stars and planetary atmospheres at energies far exceeding anything RHIC can produce. If strangelets could be created this way, and if they were dangerous, Earth would have been destroyed long before humans arrived to worry about it. Don Lincoln, an experimental physicist at Fermilab, who was part of the teams that discovered both the top quark and the Higgs boson, put it this way. When matter touches strange matter, it gets brought into a lower energy state, transforming itself from a proton or neutron into this strange new configuration. That's the mechanism. Simple energy minimization, the most mundane force in physics applied to the most alarming possible material. The good news is that the strange matter hypothesis remains unproven. No strangely has ever been detected. Not in cosmic rays, not in accelerators, not anywhere. And a 2023 analysis suggested that new calculations of vacuum energy effects might rule out stable strange quark matter entirely, but the reason we feel safe isn't because we proved it can't happen, it's because we looked around and noticed the universe hadn't killed us yet. That's a very specific kind of reassurance. Number 3, the rogue. There are, by current estimates, roughly 100 million stellar mass black holes drifting through the Milky Way. Silent, dark, emitting nothing. They don't glow. They don't pulse. They have no accretion disk to reveal them unless something happens to fall in. They are simply absent, regions of space where matter used to be and now isn't, coasting through the galaxy on the trajectories they were given when the stars that made them exploded. For a long time, we had detected exactly 0 of them. Then, in 2022, astronomers announced the first confirmed isolated stellar mass black hole in the Milky Way, designated OGLE 2011b LG0462. It was found via gravitational microlensing, a technique where the black hole's gravity acts like a lens and briefly magnifies the light of a more distant background star as the black hole passes in front of it. The black hole itself was invisible. All they could measure was the distortion in starlight, like watching a glass of water move across a table by the way it bends the image behind it. Mass, approximately 7 times the sun. Distance, around 5,000 light years. Direction, no one's going to do anything about it. But individual stellar mass black holes, as alarming as they are at least small by black hole standards. What's harder to sit with is what happens when merging galaxies create black holes at the upper end of the scale, and those black holes get kicked. When 2 black holes merge, the gravitational waves they emit are not symmetric. They come out stronger in one direction than another, and the merged black hole recoils in the opposite direction, like a gun firing. Physicists calculated in 2007 that this recoil, under the right conditions of mass ratio and spin, can reach velocities of up to 5,000 kilometers per second, fast enough to escape the gravitational pull of the host galaxy entirely. In 2023, astronomer Peter van Dokkum at Yale reported what may be the best observational evidence yet of a runaway black hole, an object with an estimated mass of around 20 million solar masses, apparently tearing through intergalactic space and trailing behind it a streak of compressed gas and newly formed stars stretching 200,000 light years. 2 million new stars, forged in the pressure wave of a fleeing black hole. The contrail is longer than 2 Milky Ways. The black hole itself emits no light, you can't see it. What you can see is everything it disturbed on the way past. It's worth noting that this interpretation is contested. Some researchers have suggested the streak could be a galaxy seen edge on. The identification is not confirmed, but the physics that would produce it is completely solid. Gravitational recoil is real, it has been observed in smaller systems, and at the upper end of the mass scale, the consequences would be exactly what Van Dokkum described. 100 million invisible black holes in our galaxy alone, coasting, waiting to be passed by, no light, no signal, no warning. Number 2, the Big Rip. In 2003, a physicist at Dartmouth named Robert Caldwell, along with colleagues Mark Kamiankowski and Neven Weinberg, published a paper with a timeline at the end, not a timeline of the past, a timeline of the future. It described in order how everything ends, 200 million years before the end. Galaxies begin to separate faster than gravity can hold them. The local group, our cluster of galaxies, including the Milky Way and Andromeda, dissolves. Galaxies drift apart and vanish beyond each other's horizons. 60 million years before the end, individual galaxies begin to disintegrate. The forces holding stars in orbit around the galactic center can no longer compete with the expansion of space. 3 months before the end, our solar system comes apart. The planets are no longer bound to the sun. 30 minutes before the end, Earth is torn apart. 10 to the power of negative 19 seconds before the end, a number so small it makes Planck time look leisurely, atoms are destroyed. Electrons ripped from nuclei, nuclei ripped apart. Every structure at every scale dissolved. And then the universe ends. Not in heat death, not in a long, cold fade, in a rip. A sudden termination of everything that holds anything together. This scenario is called the Big Rip. And whether it happens depends on the nature of dark energy, the component of the universe currently driving its accelerating expansion, accounting for roughly 68% of everything that exists, and which we understand almost entirely by inference. We know it's there because the expansion is speeding up. We know very little else. If dark energy is a cosmological constant, a fixed property of space itself, then expansion accelerates smoothly forever, and everything eventually gets cold and dark, but never gets ripped. If dark energy is something else, something whose pressure exceeds its energy density, what Caldwell called phantom energy, then its density doesn't dilute as the universe expands. It grows, and it grows without limit, until the force of expansion overcomes gravity, then the electromagnetic force, then the strong nuclear force, then the bonds between quarks, until there is nothing left to tear. The measurement that determines which of these futures we're in is a number called W, the ratio of dark energy's pressure to its energy density. If W equals -1, we're in the safe cosmological constant scenario. If the W is less than -1, we're in phantom energy territory. Our best measurement of W as of recent years is approximately -1.028 with an uncertainty of plus or minus 0.031. Right on the edge. Just touching the line. In March of 2025, the Dark Energy Spectroscopic Instrument, TPT, a survey that has mapped tens of millions of galaxies in 3 dimensions, released data suggesting that dark energy might not be constant at all. It might be changing, evolving. The significance of the signal was between 2.8 and 4.2 sigma, depending on what data you combine it with. That's not proof, but it's the kind of result that changes the way you think about everything. The problem is that scientists can't yet tell which direction it's changing. If it's weakening, we might eventually face a big crunch. Expansion reverses, everything collapses back together. If it's strengthening, the Big Rip timeline advances. Either way, the scenario that everyone had quietly assumed, that dark energy is a constant and the universe just fades, is looking less certain. Caldwell's paper ended with the observation that phantom energy would ultimately rip apart the molecules, atoms, nuclei, and nucleons of which everything is composed before the death of the universe in a big rip. The language is dry, scientific, the implication is not. We may already be in it, we just don't know which direction it's heading. Number 1, the floor might not be real. In 1979, a physicist named Sidney Coleman published a paper describing a process he called bubble nucleation. It went like this. Consider a ball sitting at the bottom of a bowl. That's a stable equilibrium. The ball has no reason to go anywhere. It's at the lowest point. Now consider a ball sitting in a small dip on the side of a hill. It's locally stable. Small nudges won't displace it. But it's not globally stable. Given enough time, or a large enough push, the ball will roll out of the dip and fall down the hill to a much lower point. Coleman proposed that the vacuum of space, the ground state of all quantum fields, the baseline configuration of the universe, might be like that second ball. Not at the bottom of the energy landscape, sitting in a dip partway down, locally stable. Not actually the lowest possible state. If that's true, then the vacuum is what physicists call a false vacuum. And it can decay. Here's how. Quantum mechanics allows for a process called tunneling, where systems pass through energy barriers that classical physics says they can't cross. Given enough time, a region of false vacuum could spontaneously tunnel to the true vacuum, the actual lowest energy state. This would begin as an incredibly tiny bubble. Then it would expand. At the speed of light, because the true vacuum is a different configuration of all the quantum fields that define physics, a different set of values for the constants, a different structure for the forces. The expanding bubble doesn't destroy matter in the conventional sense. It doesn't burn it or crush it. It rewrites the rules that matter obeys. Electrons might have different masses. The electromagnetic force might work differently. Nuclear binding might not work at all. Chemistry, the basis of every molecular structure, every biological process, every thought you've ever had, would be impossible in its current form. And because the bubble expands at light speed, it is absolutely, definitively undetectable in advance. No signal can outrun it. If a vacuum decay event has already been triggered somewhere in the observable universe, the bubble is already here or it isn't. And if it is, the first indication will also be the last. There is no warning. There is no preparation. There's not even a moment of awareness. This is not fringe physics. In 2012, after the Higgs boson was discovered at the Large Hadron Collider, physicists measured its mass and ran the numbers. The result placed the universe right at the boundary between stable and metastable, between the ball sitting safely at the bottom and the ball sitting in a precarious dip. Ian Moss, professor of theoretical cosmology at Newcastle University, described what vacuum decay of the Higgs would mean as the ultimate ecological catastrophe. Stephen Hawking wrote about it in one of his final books, noting that the Higgs potential has what he called the worrisome feature that it might become metastable, that a bubble of true vacuum could potentially materialize and expand at the speed of light. In January of 2024, an international team published results in the journal Nature Physics showing the first experimental evidence of vacuum decay mechanics, not in space, but in a carefully controlled quantum system of ultra-cold atoms in Italy. The bubble formation they observed matched the theoretical predictions. The physics is real. The mechanism works. Now here's the thing that Max Tegmark at MIT and philosopher Nick Bostrom at Oxford pointed out in a paper in 2005, and it doesn't get talked about enough. There is a built-in problem with estimating the probability of vacuum decay. If it has already happened somewhere, if a bubble is already out there expanding, then any civilization in its path has been obliterated before they could report it. We can only ever observe a universe that hasn't yet been destroyed in this way. Which means the simple fact that we exist is not actually evidence that the universe is safe. It is only evidence that we haven't been hit yet. The two things sound similar. They are not the same. The timescale for vacuum decay, as best as we can calculate, is vastly longer than the current age of the universe. We are almost certainly fine. The standard model is also incomplete, and corrections from new physics might push the Higgs firmly into the stable zone. But the conceptual vertigo of it doesn't go away with a probability estimate. Every physical law we have ever discovered, gravity, electromagnetism, the forces that hold atomic nuclei together, every constant, every symmetry, every rule that we have ever relied on to describe how reality works rests on a foundation that physics cannot guarantee is permanent. The laws of physics are not laws in any legal or moral sense. They are descriptions of how the current vacuum configuration behaves. They apply here. They apply now. In a different vacuum state, they would be different, or absent entirely. The universe does not owe us stability. It never promised anything. It simply hasn't changed yet, as far as we can tell, and we are here to notice that it hasn't. That might be the most honest thing physics has ever told us. Not that the universe is dangerous, though it is. Not that it is vast and indifferent, though it is. But that the floor we're standing on, the floor that has always been there, the floor that every experiment and observation and equation has assumed is permanent, is not guaranteed. It is, by the best reckoning we have, probably fine. Probably. That word does a lot of work in cosmology. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.